a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. How does one multiply decimal numbers? Well, for that question, we're simply going to ask, if the decimals weren't there, how would you multiply? Well, I would write this one down, and this one under it. And, of course, if there was no decimal point, this 0 is not necessary. Now, presuming that you could do this, let's us here go through it very quickly. First, multiplying by 2, you would get this, and shifting for the place I've used and multiplying by 1, we simply get that one repeated. Then having 2 placeholder zeros and multiplying by 3, we would get this, and now we would add all of those products column by column, getting our final product. Now it's going to be just that simple. Of course, multiplying long numbers is not that enjoyable because it can be messy. But we simply multiply our 2 or 3 or 4 numbers as though that decimal point wasn't there. Then we'll insert the decimal point when we're all through. And to do that, we ask how many places were there behind the decimal points total. So there's 1, 2, 3, 4. Then starting at the right end, we will count left that many places, and that's where the decimal point goes. Now let's summarize that formally for our notes. First, you multiply as if they were whole numbers. That is, disregard the decimal point. Then when you're done, count the total number of decimal places in the factors, the multipliers. Then starting at the right end digit of the answer, count off the same number of places to the left. If more places are needed by that process, insert additional zeros at the front. Now let's do one more to emphasize each of these 4 points. First, you simply multiply as though the decimal points weren't there. And of course, if that decimal point really weren't there, those zeros aren't adding to the value, it's still just 5. So multiplying the 2 without the decimal point, we would get our whole number product. Then back to the individual factors and count the number of places behind the decimal point, even if there are zeros. So 1, 2, 3, 4, 5, 6. Starting at the rightmost end, no matter what is there in your product, count forward 1, 2, 3, 4, 5, 6. And if in doing that extra places are formed, insert a placeholder 0, and that's where the decimal point of my answer goes. Now, if in front of there you want to insert another 0 just to make it easier to read, that's permissible. It doesn't add to the value, but sometimes it emphasizes seeing the decimal point. Okay, again, multiply as though the decimal points weren't there. Count the number of places behind the decimal points in the factors. Starting at the right end, count forward that many places, inserting zeros if extra places are created. Now that I'm all done, note we have 3 zeros. This 0 is necessary to tell me there are no tenths, and that forced me to realize that 2 is in the hundredths position rather than the tenth. Logically, this end zero and this front zero in front of the decimal point are not necessary to the value. So they may be kept, they may not. That depends upon the circumstances of its use. Many verbal problems can best be handled with multiplication. What is the width of a panel made from 8 board strips? So we're going to have 8 strips of boards here, side by side, of course closer together than this. 8 of them. And each board is 2.125 inches wide. So if we want the total, that means we must add 8 of these, or if you want, 8 times this one number. So we have a multiplication problem. Again, if you're multiplying with decimal, even though this one doesn't, really it does, it's back here, just multiply as though the decimal point isn't there. 8 5s is 40, carry the 4. 2 8s is 16 and 4 is 20, carry the 2. 8 1s is 8 and 2 is 10, carry the 1. 2 8s is 16 and 1 is 17. Now count the decimal places behind the decimal point. 1, 2, 3, there aren't any there. Starting at the rightmost end, count forward. 1, 2, 3, and the decimal point goes there. Now, for the value of the problem, these zeros behind the decimal point on the end do not delete from or add to the value. So I could drop those and say that the panel is 17 inches wide. Now, if you're faced with a string of multiplications, which will generally be the case in most science courses, same thing, just more work. First we'll do that, forgetting that the decimal points are there. And of course, without the decimal point, that's 2 times 300, which is 600, which we probably could have done mentally. Then that answer times the next one, pretending like the decimal point isn't there, and you would get this. Then taking that answer times this last digit, pretending like the decimal point isn't there. So 5 times my last product gives me my final multiple product. And to determine the decimal point, you go back to the original factors and count the total number of decimal places behind the decimal point. So it's 1, 2, 3, 4, none here. So counting from the right end forward 4, that locates the decimal point. 3.3, and these zeros are not necessary, except to tell somebody the degree of accuracy at which the problem was worked or rounded off. And of course, multiplying by calculator is as easy as punching buttons. Simply read it and punch. 1.7. Remembering there's a times between the parentheses shoved together. So times 0.23 times 8.7 equals, and you're done, 3.4017. To double check, you simply clear the calculator, rework it once again very fast, but not so fast you get careless, and see if your second answer corresponds to the first. If it does, we'll assume it's correct. That's simple. Let's do another problem and see if by doing it we can get a feel for why we do it that way. Now, the technique we're using is to temporarily pretend like the decimal point is not there, so this number would be 13. And if the decimal point weren't there, this number would be 2. And then simply multiply as though you had whole numbers. Then we said you counted the number of decimal places. Now note, we're not counting numbers or digits, but places behind the decimal point. So there's 1, 2, 3, don't count that. 4, don't count that. Then we start at the right end of our product answer and count forward the same number of places. 1, 2, 3, 4. And if by so doing we have created extra places, we insert what we've called placeholder zeros, and that's where the decimal point goes. Then of course in front we can add as many zeros as we want. They have nothing to do with the value, but these two have a lot to do with the value. So the question might come up is, why do I count forward the number of decimal places and not these other digits? Well, let's remind ourselves for a moment that the decimal number is really a form of fraction. This really is 1 3/10 times, and this really is 2 1/1000s. Then ask ourselves, how do we multiply fractions? Well, the mixed numbers we change to improper fractions. So it's 10 plus 3 is 13/10. But now note, by doing that, I didn't change this denominator, did I? This whole number merely changes the numerator. Okay, then times the next one. Then multiplying the tops. That's exactly what I had here, wasn't it? Then multiplying the bottoms, but since they are powers of 10, there's a special shortcut. We take a 1 and stick on as many zeros as I have there and there. So 1, 2, 3, 4. 1, 2, 3, 4. But recalling that if you are dividing a whole number by a power of 10, we want to make this smaller by 1, 2, 3, 4 places. Hence, 1, 2, 3, 4. So we're actually working with power of 10 in the denominator, and each time we multiply by a power of 10, we're giving ourselves one more decimal place. Hence, we have 3 decimal places here, and this is, through the product, going to give us one more decimal place. Now, that's not a formal proof, but does it sort of give you a feel for why we are counting the decimal places behind the decimal point and giving that many places to the answer? I hope it helps to make a little bit more sense, because sometimes it's a little bit easier to remember these mathematical processes if you can see why you're doing what you're doing. And that's important to realize, because for a beginner or one who's working too fast, it's usually the process that causes them to make careless mistakes. Always remembering that in mathematics and arithmetic, when we have a rule, there are no exceptions, even if the answer looks different. See, in this number, if I were to pretend like the decimal point isn't there, that would be the number 3, because zeros in front of a whole number adds nothing to its value. But here, if I pretended as though its decimal point wasn't there, those zeros are very necessary. That still is the number 2000. So you see, we gave you no rule that says to throw zeros away. Sometimes zeros are not necessary. Sometimes zeros are very necessary. So without the decimal point, this still is 2000. Without that decimal point, this is simply 3. And now, multiplying. Then counting the number of decimal places. See, we are not counting zeros, we are not counting digits, we are not counting numbers. We are counting decimal places. So there are 3 decimal places there and none here. So starting at the end, we count forward 1, 2, 3, and the decimal point goes there. Now that I've located the decimal point, I can ask the question, which of the finished zeros am I allowed to throw away because they add nothing to the value? In that case, this. So this product, 2,000 times 3,000th, is simply the number 6. And of course, if you're multiplying a long series of numbers, it's exactly the same thing, just more work. So we would multiply, in this case, just these 2 and forget that this even exists temporarily. So without the decimal point, this number is still 70,000. And this number, if I were to forget the decimal point, is just 2. And multiplying those, we get that. Now take that result times the next factor. Without the decimal point, that is simply the number 12. Now multiplying this times the answer, the product of what I had here, I would get this. Check me now to see if I'm not being careless. Then multiplying by 10, I would get and then adding those. And see, I'm not telling you what I'm doing here, I'm just letting you watch, because we've done so much of this now, it should be almost automatic. Okay, now this is the product of these 3. So that answer I will multiply times the next factor. And without that decimal point, that would simply be the number 4. Multiplying by that. 4 8 is 32, carry the 3. 4 6 is 24, and 3 is 27, carry the 2. And I get a 6. So all the way through when I'm multiplying decimals, it's as though I'm just reviewing my whole number arithmetic. And only when I'm done with the product do I ask, how many decimal places do I have? So there's 3, 4, 5, 6. And of course none here. Starting at the right end, I count forward 1, 2, 3, 4, 5, 6, and insert the decimal point. Then if I don't need these zeros for whatever I'm going to use the results for, I can now throw these away, because behind the decimal point on the end, extra zeros do not contribute to the value of the number. And one does not go very far in any school, particularly a technical school, before you realize that decimals is indeed the most basic language of all technology. You find many problems like this. Let's see, we have a rectangular microchip. Well, rectangular means it's shaped like this. It's 0.035 centimeters wide. That's very, very tiny. When you figure that a centimeter is about the width of your thumbnail. So this is 3/100ths that width, just a bare line's width thick. And it's about 72 1,000ths of a centimeter long. And what the problem needs to know is what's the surface area of this microchip. So at this point we're talking about area, and we have been given a width and a length. So you ask yourself, what do you know about the area of a rectangle in terms of width and length? And if you knew, fine, write it down. If you don't know it, then now you know exactly what you need to look up in a textbook. At the back of the textbook, usually you have formulas needed in the textbook. And you find that the area of a rectangle is the length times the width. So the formula is telling you what to do with what you know in order to get what you don't know. And can you see that these are nothing more than the variables of our algebra review? Only now we know what the variables stand for. A is for area, L is for length, and W is width in this case. And the formula is just that. It's telling you the form you need to use with your known quantities to get to the unknown. So it's telling us to find the area that we want. We take the length, which is 0.072, and multiply that. That's centimeters, by the way. Multiply that by the width, which is 0.035 centimeters. Now, if we had a calculator, we would do this with a calculator. If we didn't, we simply use the review knowledge of this lesson. Without the decimal point, this is the number 72. Without the decimal point, that's a number 35. We're going to multiply, so we simply multiply this by the usual method, and I'll just do it quickly here without you. Get your product, then count the total number of places behind the decimal point, in this case 6. Starting at the right end, count forward 3, 4, 5, 6. Insert your decimal point. Also insert placeholder zeros if extra places have been created. And so my area is 0.00252, and this 0 now is not needed to the value. But also note, on our laws of exponents, to show anything times itself, we use an exponent 2, and we read this as square centimeters. So we have this many square centimeters of area on that microchip. Very tiny area. You can see it's just slightly larger than 2/1000ths of a square centimeter. Very tiny. That last problem should really emphasize that we as students should become more and more comfortable about the necessity of looking something up if we don't know it. But how do you look something up if you don't know it? Well, the wording of the problem should give you an idea. For instance, in this one, we're talking about an area because it tells us. Furthermore, it's the area of a circle, and they've given us the radius of a circle. So, drawing a sketch to see if we know what it is we're talking about, well, here's a circle, and a radius is the distance from the center to the circle. So they're saying the radius is 4.025, and this m, you should now know that that is the abbreviation for a meter. So now our question is, what's the relationship between area, which I'll call A here, and radius, which I'll call R? If you don't know this, then at least you know exactly what to look up. And most textbooks, like the one that goes with this series of tapes, at the back they will have a list of formulas for perimeters and areas. And so you simply scan the formulas, in this case pictures as well, until you find the picture of what it is you're talking about, in this case a circle, and find an area. In this case it gives us two areas, one in terms of the diameter and one the radius. This is so small on the screen you perhaps can't read it, but it says the area is a funny symbol which we've learned to call pi times radius squared. So writing that down, area is pi times radius squared. Well, we know what this means. This means take two of these and multiply together and multiply by this. And if you did not know what this was, you would look it up at the back of the same textbook. And it is the decimal number approximately 3.14. Actually, there are more digits here, 3.1416 if you want more, times the radius, which is 4.025 squared. Then if you wish to do this by hand, that's fine, or with a calculator. So using our calculator here, and if you check on many scientific calculators, the value pi is already there to much more accuracy than even this. On my particular calculator, there is a button right here, which I get by pushing this one and that one. And see, there is pi to lots of places. Then times the radius. So times 4.025. Now I'm doing this a harder way than is necessary if you are comfortable with a scientific calculator, which many of you are not. I'm going to actually multiply it times another pi, 4.025, because this says take two of those and multiply them. Then finally equal, and rounding to whatever accuracy is required for your problem. Let's say in this case to the nearest hundredth, this would be 90 square meters. And in this case, I kept this 0 to let whoever know it that that's indeed a rounded accuracy, that that's actually accurate there. And I am done. Let's really zoom in on this calculator a little bit more. Just above this key that says EXP is my pi. We'll zoom in a little bit more in just a moment for you to really see it. This is what's called a scientific calculator, and we're going to be referring to this particularly in the next lesson. So if you have one for the next lesson, you may wish to borrow it. There, perhaps that's a little bit better. Now you can see the pi above the EXP key, and to get that pi, I push this button here first, which tells the calculator read what's above rather than what's on the key. However, in the next lesson, we're going to play with this key itself quite a bit. So if you have a scientific calculator, bring it with you to the next lesson. If you don't, it's really not necessary. So don't make a special effort to purchase one. While we're at it, you might notice that on a scientific calculator there are lots of extra keys. And these are keys that normally you don't use unless you get up into college math or some very, very technical subjects. But a scientific calculator really is not that expensive and sometimes very useful. Okay? This is your host, Bob Fennell. We'll see you at that next lesson. Good luck.